we're about to work through a practice exam. Now, before we start, let's say a couple things up front. One, this is practice. Sometimes these problems are a little bit harder, and they're not going to be the exact same type of problems necessarily. In fact, that's not the goal of a practice exam. We're not here to say, aha, here's the problems, and you don't need to study anything else. We're here to say, here are some problems that could be sort of give you a sense of what to expect. So as we go through, we'll talk about ideas, we'll highlight processes, but don't get so narrowly focused and say, well, I have to only know these things. Make sure you know many things. Practice many things. Study many things. Now, we're going to have a formula sheet, and I have a copy of it here. Now, during the exam, pro tip, if you want to use the formula sheet, there's this way, it's called you take it off the back. So that way you don't have to keep turning the exam over. No, just have it handy. And for us, we're going to be in this section of the formula sheet. That's applications, and I should also mark here polar coordinates. So that's where we're going to be putting our time and energy. At the same time, we might need to know some trig. Well, if there's polar, it's probably a good chance we'll need to know some trig, and we need to know our basic derivatives and integrals. So that's the portions of the formula sheet we'll be using. Those are the ideas we'll be testing. Now remember, the formula sheet is not some magical wand. We don't wave the formula sheet over the test and suddenly all the answers appear. It's a tool. And as with all tools, you get better at using it with practice. And the more practice you have, the better you'll get. So make sure you put in the practice. Invest in yourself. Believe in yourself. You are worth investing in. And so let's go ahead, work through these problems together, and let's have fun. All right, here we go. A solid lies on top of the half-circle region in the plane described by -3 less than or equal to x less than or equal to 3, and 0 less than or equal to y less than or equal to the square root of 9 minus x squared, a half circle. And it's a half circle of radius 3. And it's this blue thing here. You'll notice we're not looking at the plane from above. We're sort of looking at it askew because we're going to now make a solid. So what can we say? Well, given that the slices taken perpendicular to the x-axis of the solid result in squares, with one side of the square lying in the region, then find the volume of the solid. All right, so we're slicing this solid, and that's what's being illustrated here. We see a slice taken really clearly here. So here's this one slice highlighted for us. I say, aha, it's a square. And we see, lo and behold, there's this portion of it is down in the circle. Now, what's going on? Well, if we do look at this from above, then what we're seeing here is we see our x and our y, and our slice would be roughly here. You say, okay, so here, this length is that length. And so now we say, okay, so in terms of this square, it says, well, this is a square, and the side length is the length from the axis to the curve. So that's the square root of 9 minus x squared. But being a square, that also means that this side is the square root of 9 minus x squared. And so now our great aha says, well, how do we find the volume of such a thing? It is part of our formula sheet. In fact, it's the very first application we talked about. So when we have a solid described in terms of cross-section, we say, well, volume is the integral of the area. And then the width is like a little thickness. In this case, it'll be our dx. So we say, okay, so volume adding up -3 to 3. Okay, so -3 to +3. And then we're going to have the area, well, it's a square, so it's the length times width, square root of 9 minus x squared dx. All right, and there we go. So this is area, width. All right, well, and we can say this is the same as integral negative 3 to 3, 9 minus x squared, because we have a square root and then we're squaring it. And we're pretty much home free. We can make it a little bit easier on ourselves. This is an even function. We're going from negative a to positive a, so we can just double integral 0 to 3. Make sure it's even before you try to do this. And now we say, okay, great, that's 2 times 9x minus 1/3 x cubed. Evaluate 0 to 3. All right, well, that's 2. And when you plug in 0, you get 0, so we just need to plug in 3. 9 times 3 is 27. 1/3 times 3 cubed. Well, it's like 1/3 times the first 3 goes away, and so it's really 3 squared. So it's 9. 27 minus 9. And 27 minus 9 is 18. And times 2 gives us 36. So there we go. Now, is that one of our options? It is. Nice. And there we go. So the answer is 36. They might have said, well, wait, I thought volumes always had pi. And no. When we do volumes of revolution, pi is often involved, but this isn't a volume of revolution. I said, well, what about the fact that it's a circle? Doesn't mean that pi is going to be involved automatically. It depends. So don't be like, it must be one of these ones with pi's. No. We have some options which are very tempting. Don't give in to temptation. All right, so I'm just going to put a little note here just for reference. This is our basic tool that we used, and there we go. One last comment before we leave this problem, and of course, we'll take our time. This is meant for us to enjoy things. So the last comment is to say, how do we recognize these types of problems? So we recognize these types of problems when it goes through great lengths to describe cross-sections. So whenever it talks about volume and you spin, you're like, okay, volume of revolution, then you're into either wash or shell, kind of situation. But whenever it says, oh, it looks like a square or a triangle or a half circle or things like that, when you see them taking great lengths to describe cross-sections, you say, I just need to say, how big is the cross-section for a particular slice, add that up times, the dx, and there we go. All right. So, hey, not so bad for our first problem, but of course, more to come. The graph of a polar curve, r as f of theta, is shown below. And so there it is. That almost looks like a pair of glasses. And all right, so select the function being plotted from among the choices given. And so we have a bunch of possible candidates. One of these is probably right. One of them has to be right, but most of them are going to be wrong. Now, we don't want to spend a lot of time. Now, this is a case where we can oftentimes eliminate things fairly quickly. How can we eliminate things? Well, we start thinking about things that we should expect. Look for convenient angles. And in particular, convenient angles are when are you back at 0, and also angles easy to plug in. And of course, think about symmetry. Symmetry is a very useful tool. Now, let's look at this first option, sine of theta. You say, well, let's take a very convenient angle to think about. What should happen at theta equals 0? Well, when you plug in theta equals 0, you should get sine of 0, which is 0. And now, technically, you should also say, well, what about the other side? Because, of course, there's this fancy thing of going backwards in polar. But even if you plug in pi, sine of pi is 0. So the problem is, I should not be able to see anything away from the origin along the x-axis, but I'm seeing things. So what does that tell us? Well, it can't be A or B, because we see that sine theta being involved. What about cosine squared theta? Now, cosine squared theta has this very nice property, because cosine theta is an even function. So what's going to happen is if you look at cosine squared of theta, it's the same as cosine squared of negative theta. Now, what does that tell us? Well, it tells us that this graph would have to be symmetric. And namely, it would have to be symmetric across the x-axis. And I'm seeing here, I forgot to make some notes. So I'm saying things, but I should also write things down. So, okay, all right. These first two ruled out by plugging in 0. So, now, back to our discussion. Is this symmetric across the x-axis? No. Okay, so C is out. This is ruled out by symmetry. Okay. Well, that leaves us with a 50-50 chance. And D versus E. Now, what can we do? Well, let's look at, again, think about convenient angles. Sine theta minus cosine theta. Well, what angle is that? Well, where we get 0. When does sine equal cosine? And the answer is at 45 degrees. So now the question is, if I go out 45 degrees, am I at the origin? And if I'm not, you'll see here, we're not, then it can't be that. And so we say, okay, this is ruled out by theta equals 45 or pi fourths. And so, what does that leave us with? It leaves us with D. And lo and behold, now you can go through, you can test a bunch of angles, but we're fine. We don't need to test any more angles. We just have to do enough to make sure we have the right shape. So here, rule things out. And that can oftentimes be a lot faster. Remember, when we're doing multiple choice, we don't always have to prove that our answer is the right one. We only have to prove that all the other answers aren't. And we don't have to justify as we go through. And so keep that in mind, especially if you see problems involving graphs. Think about what you can do. How can I rule something in? How can I rule something out? Again, look for convenient angles, look for symmetry, and usually between those two things, you can get the graph pretty quickly. So don't panic, just plot a few points, right? Yeah, we got this. No problem, no problem. A triangular piece of glass, 5 feet wide at its base. Okay, so this is the triangle. And so it's 5 feet wide at its base and 3 feet high. And you see they've marked here some numbers. You can see 0 to 3 is in fact 3, so that's good. Is installed as a viewing window into a tank where the top of the triangle, so there's the top of the triangle, is 2 feet below the surface of the water. And it says see the picture below. Given that the water has weight density 60 pounds per foot cubed, set up an integral in terms of y, where y is as marked in the picture to determine the force pushing against the glass. Now notice they gave us y. That's one of the things you often have to decide when you're doing a problem that's a word problem. Things like a pumping problem, a force problem, a lifting things problem. And they all come down to say, okay, where should you put 0? Which direction is increasing? Now, ultimately, it won't matter, but some are simpler to work with. And in this case, they said, hey, let's put 0 at the top of the triangle. And putting 0 at the top of the triangle is a smart choice to do because we're going to do some various manipulations. And if you ever have a triangle involved or a cone, putting 0 at the tip is going to be very convenient for us. All right, so what do we do? Well, we can look up our force. It's one of our formulas. It's right here. So we'll put that for reference. So we have that force is adding up, integrate A to B. We have our density, our depth, our width, and our height. All right, so there we go. That's the force. And now that's from our formula sheet, and we start filling things in. Okay, do we know the density? Well, yeah, we have it, 60. And so it goes here. Now you might want to say, aha, 60 I'll grab the only thing that has a 60, must be E, right? Well, hold on, there's other things involved. Okay, so now let's talk about depth. Now, what's going on here is we're thinking of taking a small piece. So here we're taking like a small strip, and now this is at some y. We don't know exactly what. So then the depth says, well, how far down is that from the surface of the water? Okay, well, so in other words, how far is it from y to -2? And keep in mind, you have to keep track of sign. And so we say, well, the distance would be up to y would get us to the top of the triangle and 2 more. So depth, y plus 2. All right, good. Now, the height, that's the easy one. It's a little tiny thickness. So the height is your dy. So where are we going to put a lot of energy into this problem? Well, we're going to be putting the most energy into this problem in the width. And so let's talk about how do we get the width. And here we say, well, the width varies with depth. When we're at 0, we're width 0. When we're at 3, we're width 5. Now, there's a couple ways we can think about this. We can do some reasoning, but instead of just reasoning, we can actually take advantage of a certain situation. Look at what you have here. You can think of it as 2 triangles. This small triangle and this big triangle. And these triangles are similar. Okay, so what's the punchline? Well, when you look at what's going on here, so I'll draw it again. So you have 5 and 3, that's the big triangle. And then here you have a y, that's the level that we're taking our slice at, and w for width. Now, the moral here, w is to y, right? This horizontal distance, vertical distance, w is to y as, or equals, 5 is to 3, 5 thirds. Okay. Or we can say, aha, w is equal to 5 thirds y. So that's what goes in to the width part. Now, notice it's pretty clean. And the reason it's pretty clean is because of where we put the 0 at. And putting the 0 at the tip of the triangle, or if you're doing a pumping tip of the cone, will make these pieces nice. And we like nice things. It helps simplify this. There is one other thing we should talk about, which are the bounds, because integrals need bounds. So again, we're going from y. Where is the window? Well, the window is between y equals 0 and y equals 3. So 0 to 3. So recapping here, put it all together, and what do we have? Well, we have the following. We're going from 0 to 3. Okay, good. And, well, that doesn't knock much out, but it knocks e out. 60 times 5 thirds. Well, 60 divided by 3 is 20 times 5 is 100. Okay, so we need 100. Well, that rules c and d out. All right. And then we have y plus 2 times y. And that's y squared plus 2y dy. And so we need 100. Y squared plus 2y dy. And that is a. Oh, yeah, a. Yeah, sure. You betcha, a. And there you go. There you go. All right. Wonderful. And this type of problem is not so bad. You just have to say, look, think about the formula, and then start filling in the pieces. Be ready to use similar triangles. And hopefully, fingers crossed, you have nice instructors who will tell you, hey, put 0 here and follow this orientation. Because most people look at this and say, are you allowed to have increases as you go down? Yes! Yes! You're perfectly allowed. And so don't stress too much about that. Trust them. They care about you. Your instructors love you. All right, well, let's keep going. Which of the following integrals gives the length of the polar curve r equals 2 plus secant theta, where theta goes from 0 to pi over 4? Now, there's 3 times that length shows up. And so if we pull up our formula sheet, we have it as 1, 2, 3. So what's the difference? Well, this first one, this is y equals f of x setting. We're not in that setting. The second one, this is parametric, and we're not in that setting. The last one down here is polar. Hey, we're in polar. Now you might say, well, how did you know you're in polar? Well, they told us. It's subtle, but we were able to pick up on that. So we say, all right, well, now we know which version of the length formula that we need, and that's going to help us out. So let's write it down here for reference. So it says our length is going to be the integral alpha to beta of the square root of, and then we have our f of theta squared plus our f prime of theta squared d theta. Okay, now put that aside and get back to our regularly scheduled problem here. Well, we have here our f of theta. So here's our f of theta. Now let's get to work. So according to this, we're going to add up. We have our bounds, 0 to pi over 4, and they all have 0 to pi over 4. And now what can we say? What's the square root of the original function, 2 plus secant theta squared, plus, now take the derivative. Well, the derivative of 2 is 0, and derivative of secant is secant tangent. And we take the derivative because it says take the derivative. So secant theta tangent theta squared d theta. All right, well, it's not quite looking like any of these yet. That's all right. We're allowed to rewrite. Okay, so this becomes 0 to pi over 4, the square root of 4 plus 4 secant theta plus secant squared theta. And that's if you expand the first part. I know, algebra? They want us to do algebra? Of course. Most of calculus is algebra. You know, what we think of calculus is just that light candy coating that just makes everything so much sweeter. But definitely make sure you get your algebra down. All right, plus, and then secant squared theta, tangent squared theta. All right. Now, looking at this, it's not like exactly like any of them, but I will say some seem more likely than others. And I see a 4 and a 4 secant theta. I see E has both of those, and this has 4, but not 4 secant theta. And this kind of has a 4 and a 4 secant theta, if you bring the 2 in. But then there's this other stuff, and I highly doubt that's 0. But let's see, what can we do? Well, we can use our knowledge of trig. Okay, so what's some things that we can say here? Well, notice on this last part, you can pull out a secant squared. So you have secant squared theta times 1 plus tangent squared. And you're probably thinking 1 plus tangent squared, that sounds familiar. Well, let's take a look. And, 1 plus tangent squared is secant squared. That is familiar. In fact, it's really convenient. So this is the same as secant squared. So it's really secant squared times secant squared, which is secant to the 4th. So, it is what we think it was. So we have the 4 plus the 4 secant theta plus secant to the 4th theta d theta, which is exactly E. All right, so E is the right answer. All right, beautiful, beautiful, nice. Okay, now before we leave this problem, let's point out some things that some people might be tempted to do, and we're going to say it out loud. just to say, but we would never fall for that trap. Now, what happens? A lot of people, when they see square roots involved in squares, they say, oh, the square root and the square cancel. And then you'd have, 2 plus secant theta and secant theta tangent theta. The problem with that is that plus sign. Plus, or in other words, addition and exponentiation, or taking something to a power, does not mix very well. They do not get along. So you have to be very careful. So be careful. As much as it's tempting to say, the square root and squares, things go away. When you have those plus signs, no, more work, more work. And I also want to point out one other thing here. So that's why A looks tempting. C is also tempting. Why? Well, remember how we said, what's the derivative of 2 plus secant theta? Is secant theta tangent theta? So this would be the square root of 1 plus f prime squared. Now, why is that tempting? Well, if you go back to the formulas, you'll see 1 plus f prime squared is the length if you were y equals f of x. However, that's when you are in Cartesian, not polar. So you want to make sure you're using the right formula. And if you're using the wrong formula, well, they're going to tempt you. Because, they've been doing this for a while. They know the kind of mistakes people make, and they tend to show up quite frequently. So pay attention and make sure you're in the right setting. You have time. Slow down. Catch your breath. Look for clues. If you see polar, you say mindset, polar. Focus on the polar. If you see Cartesian, boom, make sure that's your mindset. You can do it. You can do it. For which of the following values of q will the tangent line to the polar curve r is equal to q minus cosine theta at the angle theta is 1/4 pi over 4 be vertical? Okay, so we have this curve, q minus cosine theta. Now, we don't actually know what it looks like because it depends on q. By changing q, you change what the curve does. So we can't really graph it. So we say, okay, but that's okay. We can think about what's going on. Now, we have a couple of clues. We know we're after a tangent line. All right, so that's something. We know we're working in polar, and then there's a really good clue, which is to say we want our tangent line to be vertical, a vertical tangent line. All right, so when is a tangent line vertical? Well, let's for a second put aside polar and say, what if we were doing parametric? So a quick parametric side note, or we could say it's a parametric side quest. And we'll see this is actually a good thing to look at. Well, what can we say? The derivative dy dx looks like you have your y prime divided by your x prime. And now, vertical means you're going straight up and down. So your y is changing, but your x is not changing. And so we say, we want to make sure our x prime equals 0. So when we see a tangent line being vertical, that's code for, hey, make sure your x prime is 0. If you wanted a tangent line that was horizontal, what would you look for? Answer, you'd want the y prime to be 0. And just as a fun side note, one of these options will actually give you a horizontal tangent line. I'll let you figure out which one later on. But okay, so what can we do here? Well, we say, all right, we want the x prime to be 0. But wait, that was parametric, we're in polar. But here's the thing. When we're in polar and we're working with curves, what we can do is we can take a polar curve and we can turn it into a parametric curve. And the way we do this is we say, well, we have our function of r in terms of theta. So what we'll do is we'll set x equal r cosine theta and y equals r sine theta. So in our case, r is this q minus cosine theta times cosine theta, and y would be q minus cosine theta times sine theta. We don't need to keep track of y anymore because we already know what we're looking at. We only need to focus in on that x prime. All right, so our next step, what is x prime? And let's set it equal to 0. Remember here, q is like a number, so the only thing that changes is the cosine. So we have the following. We have x prime. That's the derivative of the first. Derivative of q minus cosine. Well, derivative of cosine is negative sine. So that would be sine theta. And then times cosine theta. So the derivative of the first times the second. Plus, now we have the first, q minus cosine theta, times the derivative of the second. And the derivative of the second, well, that's negative sine theta. All right. Well, great. Now, what are we going to do? We're going to plug in pi over 4. Okay. Now, for reference, we have this table. And so we can say, aha, we know how to plug in pi over 4. It's all right there. So if you don't remember, don't panic. Just use it when you need it. Root 2 over 2. So at theta equals pi over 4, we're going to get that 0 is equal to, because remember x prime needs to be 0, we have a root 2 over 2 times a root 2 over 2 plus q minus root 2 over 2 times minus root 2 over 2. Okay, cool. And, well, if we start multiplying this out, root 2 over 2 times root 2 over 2, that's 2 over 4, which is really a half. And then we have minus root 2 over 2 times q. And then here, we're going to get minus root 2 over 2 and a minus root 2 over 2. That again makes plus 2 over 4, which is another half. And so we say, okay, well, that's looking good. And that becomes, if you move things around, so we can move this to one side, put the halves together, root 2 divided by 2 times q equals 1. And by the way, root 2 divided by 2 is another way of saying 1 over root 2. So 1 over root 2 times q equals 1. And so our conclusion is q should be square root of 2. And there we go. All right. And it's an option. Woohoo! Nice! Now, we could also have done other things. We could have plugged in root 2 and say, okay, which one works? And, sometimes it takes a while. And so there's different approaches. Make good use of your time. You have a lot of problems. And so what you want to do is say, hey, I want to make sure I'm doing a problem effectively. Some problems can be done quickly if you think about them a little bit, and other problems take some time. And of course, as always, it's okay to say, I'll come back and revisit this one later. No worries, no judgments. Do what works for you. This is your test, and you should enjoy it. All right, well, let's keep moving right along. Our final multiple choice. Let R be the region bounded by the y-axis, that's this axis here, and the parametric curve t minus t cubed comma sine pi halves t, where t goes from 0 to 1. And so that's going to be this piece here. And they put an arrow here, so that can be a little bit useful. We'll talk about why that might be useful in just a moment. And all right, the question. Which of the following integrals finds a volume using the washer method when the region is spun around the y-axis? Okay, all right. Cool. Now, we see where it's spinning. They gave us a convenient arrow here. Good job, them. I hope they keep doing that. That's really lovely. We know we're doing washer method. All right, now that can be helpful. So, how are we slicing? Well, if we were slicing in a vertical way, we would not be making washers, we'd be making shells. If we slice horizontal, then yes, when we spin, we do make washers. So we say, all right, great. So we're going to be slicing in this way, and these are what we're going to spin. All right, now, okay, let's talk about the formula. When we had our y equals f of x, we said, look, we have a formula for washer method. It's right here. What formula to be used for parametric? It's right there. That's how powerful these formulas are. They're built to actually work in multiple settings. And you just have to say, be ready to adapt. All right, so I'm just going to copy this down. Pi, we have our big radius squared, subtract our little radius squared, and our width. Okay, so now we're ready. First, some good news. We say the washer method, but actually we're going to be the disk method, because notice we're going right up to the y-axis. And so our little radius is truly little, and it's 0. Whew. Okay, now let's think about some other pieces. What is this going to be? Well, that is this distance here. You say, oh, well, generically, keep things simple and then start filling in. That is how far over you are to the right, and that is your x. Now, how are we going to actually integrate? Because we're parametric, everything will be in terms of t. So we say, okay, we're going to put our bounds in terms of t, and that makes 0, 1. And so then our x, that would be our t minus t cubed, and then we're going to put that in here, and we're going to square it. So we say, okay, we're looking for something 0 to 1, and then we have our pi, t minus t cubed squared. And at this point, if we were impatient, we might say, oh, look, that's a. When we're done, right? But we're not impatient. We are calm. We are calm like a summer day. And we say, hold on, there's a term here. The width. Now, you might think, well, yeah, isn't that dt? No! So you have to be careful here. Remember, t is a parameter. I often like to think of it in terms of time. So dt is not a measurement of distance, so it can't be used for a width. Width is a distance measurement. And so that's where you have to pay attention. So you say, okay, well, if it's not a distance measurement, how do you turn it into a distance measurement? And so now is where we say, well, what's going to happen is really this part right here is a small change in y. That's how we think of it. So we need to say, how do we write this small change in y in terms of t? Well, we know how to write y, so the small change in y means that this width will become y prime of t dt. So this is our, another way to say this is our dy. All right, so let's make sure we're careful. Okay, so we have our y prime. Here's our y. What's our y prime? Well, the derivative of sine is cosine, and leave the inside alone. Then chain rule, you will need another pi halves, and there will be a dt. Okay, so that's our width. And now we have all our pieces together. There's one small subtlety. Normally this is not such a big deal, but I want to point it out just in case. You never know. You never know. The small subtlety is, how do you move along the curve? If we're moving, down up, then dy is positive and we're good. If we're moving up down, dy is negative, we'll be off by a sign, And so then we would say, oh, make sure to correct it and put in a minus. So sometimes with parametric, you get an orientation issue. The only thing that ever affects is a plus or a minus. And so the only thing you have to think about is what's happening with this dy part. And so we say, well, hey, they conveniently gave us an arrow. Change in y, because we're going upwards, it's positive, so we're good with this sign. We don't need to throw in a correction. In other words, we don't need to add a minus sign. And we're basically done because we say, hey, check it out. We see a pi over 2, meaning we better have a pi squared over 2 in the front, and only one of these has a pi squared over 2 in the front. So unusually for us, it's the oddball. But okay, if we put it all together, just for completeness sake, 0 to 1, pi times pi over 2, pi squared over 2, r.t minus t cubed quantity squared, cosine pi halves t dt. And yes, we have all the pieces are there. So the answer to our final multiple choice is C. All right, good. Set things up. Yeah, all these formulas we learned, we can put them in parametric, we can put them in polar, we can do all sorts of things. Just make sure you understand how these things translate. And then you'll be great. You'll be wonderful. That's the end of our multiple choice, but don't worry, the fun continues. Let's move on and do our long answers. Let R be the region described by x goes 0 to 1 and tangent pi fourths x less than or equal to y less than or equal to square root x. And it's this region right here. Consider the solid form when this region is rotated about the line y equals -1, and you'll see they put a little. Okay, so that's where we're spinning. So we'll go ahead and mark it here. Hello, y equals -1. Set up, but do not evaluate. Oh, these are some of the sweetest words when it comes to a calculus exam. So it's about setting things up. The integrals to compute the following. The volume of the solid using the shell method. Now notice here how they were very specific. And they didn't say, oh, just find the volume. They said, find the volume this way. You've got to do the shell method. And if you want the points, you got to do it what they ask. So we're going to make sure we use the shell method, which is good. We haven't had a chance to try the shell method yet. So it's like, all right, now we have our chance. We're going to flex our shell method muscles here. Okay, so let's start with A, and then in B, by the way, just to preview, we're going to do surface area. All right, now, first off, shell method. We have to ask the question, how are we slicing? So if we think of it, hey, they gave us as functions of x, why don't we use functions of x? That would be a vertical slice. Now, what happens if you have a vertical slice? Well, what shape do you form? Just sort of visualize it, right? We have pens, we might as well use them. Vertical slices lead to washers, not shells. What if we did horizontal slicing? What shape are we forming as we spin? Shells. Shells, by the way, mean cylinders. So you see we form these nice cylinders as we spin. So our great aha, we're going to have to slice this way. All right. There we go. Now, the other great we have to be really careful here is because we're slicing horizontally, that means we're going to integrate with respect to y, because we're having small changes in y. Horizontal slices integrate with respect to y. Vertical slices integrate with respect to x. All right. Well, what does that mean? It means we have to rewrite our functions. So we say, okay, we need to have these functions. be rewritten in terms of x equals. Now, some are easier than others. Here, how do you get rid of the square root? Well, y squared. Great. No problem. Okay, now here, tangent's inside. X is inside the tangent. So we got to get it outside the tangent. So what gets rid of the tangent? Well, the inverse of tangent, or the arctangent. So this says, hey, this is really like arctangent of y is equal to pi force x, or we could say x equals 4 over pi arctangent of y. And, it just wouldn't feel right to have an exam practice without a little bit of arctangent. So this is good. I like that. All right, good. So, and one other thing we should comment, we were told about x, we should also figure out y. So when we plug in 1, and we can plug it into either 1, what happens with y? Well, what is the square root of 1? 1. What's tangent of pi force? 1. So we say, oh, well, that's very convenient. It won't always be that way, but let's enjoy it while we can. All right, so we're ready. So for part A, volume by shell method. Now we have the generic formula, 2 pi radius height width. So I'm going to write that down. And so we have for part A, our volume is 2 pi, adding up A to B. We have our radius and our height and our width. But because we're doing vertical slicing, I'm going to just switch it to width and height. And let's talk about all these pieces. Okay, so for the height, that's your dy. No worries. A and B, well, those are your bounds. Where does y go from? 0 to 1. Great. Lovely. All right. What about the radius? Okay, well, this is at a particular value of y, and we want to go and say how far is it from an arbitrary y down to -1. Y gets you to the axis, but then you have to keep going one more. So it'll be y plus 1. Another way to say it is take y, subtract -1, a difference. And so that's how you can find radius. And of course here, notice that where we're spinning is below. We could have spun someplace above, again, but we take a difference, but then in that case, take large value minus small value. It's always large minus small. So y subtract -1. So our radius here is y plus 1. Now, what's our width? Width is how far across you are. And so it's a difference. Again, large minus small, right minus left. Okay, so what's the curve on the right-hand side? The arctangent one. What's the curve on the left-hand side? The y squared one. So the width, well, I want to make sure I give myself enough room. The right, 4 over pi arctangent of y, minus the left, y squared. Okay, now we have all our pieces, and we'll just write it out and say, all right, this becomes 2 pi integral 0 to 1 of y plus 1 times 4 over pi arctangent of y minus y squared dy. And remember, we just had to set it up. We don't have to evaluate it. Whew. Good. Good. So that's good. So we're done with part A. Well, that still leaves us with part B. The surface area of the solid. All right. Well, now we're going to go through and do the surface area. And when we think about doing the surface area, we'll say, let's split it into sort of two parts. We'll say, let's figure out what's the surface area, or say just when we spin that part corresponding to root x, and let's also do the surface area when we spin this part corresponding to tangent of pi force x. Now, I'm going to make a comment. What should you integrate with respect to when finding surface area? With respect to x or with respect to y? And the answer, yes. and what I mean by yes is you can do either. And because the surface area, we're not doing vertical slicing, we're not doing horizontal slicing, we're cutting up the curve. And so we don't have to worry about, oh, dx or dy, because surface area has this aspect of length. So let's make some notes here. We have our generic surface area, 2 pi radius length. But when it comes to length, there's 3 variations of length. We are in the y equals f of x variation. So what can we have? Well, let's start making notes here. So for part B, we'll have surface area is we have 2 pi add up a to b of radius and length, where length is square root of 1 plus f prime of x squared dx. Now that's if you integrate with respect to x. Something similar if you integrate with respect to y. I'm going to go ahead and do it with respect to x. I have no problems with that. And but if you did it with respect to y, you'd have a different formulas. You get the same answer. You get the same points. All right, so we're going to do 2 of these. And so let's work through it. Now, before we do that, I should just make one other comment. So when we think of slicing, so here it's like, boop, here's a little slice of just that part. And so really you should think of this as I have an x comma y, and when we talk about the radius, it's how far away you are. So if we're integrating with respect to x, then our radius would be y plus 1, and where you replace y with the appropriate function. On the other hand, if we integrate with respect to y, our radius would be y plus 1, and then you wouldn't have to do a replacement. But all right, so here we go. We're going to add up 2 parts. I'll do the top part first, doesn't matter the order. So we have 2 pi integral 0 to 1, and our radius is y plus 1. Y is root x. So root x plus 1 times the square root of 1 plus the derivative of root x. Well, that's 1/2 x to the minus 1/2 squared dx. Okay, 2 pi add up radius length. That's that part. So we'll make some notes here, and this is the root x portion. Okay, now plus 2 pi integral 0 to 1. Okay, and now we're doing the tangent portion. So y plus 1 becomes tangent pi force x plus 1. There's our y plus 1. Square root of 1 plus, what's the derivative of tangent? Well, it'll be secant squared pi force x. But don't forget chain rule. You're going to multiply by a pi force. And now that's being squared. You might say, well, wait a second, we already squared secant. No. You got to square the derivative. The derivative just happens to involve a square. And don't forget the dx. And then, okay, so that's our tangent pi over 4 portion. Okay, well, tangent pi force x portion. And so we just have to put them separately. And now, finally, we say our answer is the sum of these together. And there we go. And it's okay to have multiple integrals. That's one of the things that they hinted at. Could be multiple integrals. And all right, there we go. Life is good. We did it. And we have these terrible integrals. And oh, thank goodness, we don't have to solve. Oh, phew, good. Made me a little nervous. All right, let's get going. A leaky bucket is pulled up to a height of 40 feet by a chain attached to a pulley which is anchored 50 feet off the ground. Okay, so maybe let's draw a rough picture here. So we have here our pulley, and this is anchored 50 feet off the ground. So we'll put 50 feet here. We'll put ground level, y equals 0. And so this is the pulley is doing the work. And we have this chain, and there's this bucket. You might say, how do you know that's the bucket? Well, good question. I'll write the word bucket, and you're like, oh, I see what you mean. That is indeed a bucket. And but it's a leaky bucket, right? So, okay, so maybe it's water, and water's falling out. So there's the leaking part. Okay, so now we have our picture. And all right, and keep in mind, we're not going all the way up. We're going up to a height of 40 feet. So we're stopping a little short. We want to get up to 40. So we're stopping at that level. Okay, at ground level, the bucket weighed 600 pounds. But when it reached a height of 40 feet, it weighed 400 pounds. So we lost 200 pounds out of the bucket. And but at least we got something, so that's good. Now, assuming that the bucket lost weight at a constant rate as it moved up, and that the chain connecting the bucket to the pulley weighs 5 pounds per foot, then determine the work done in lifting the bucket. Include units in your final answer. And the thing about include units in your final answer is when you see that, you say, great, I just need to remember at the end to put that in, and I get a free point. Because almost always it's going to be like 1 point is including units, but we want to make sure to put that in. We don't need to include them in our intermediate step. What's our formula? Well, this is a work problem, and there's two variations. There's a special case which looks long, and that's for pumping. We're not pumping, we're lifting. So work is adding up force times distance. All right, so there we go. So our basic problem is work is adding up our force times our distance. And so for us, we're going to have to figure out what these things are and put it all together. Now, it turns out most of this is pretty quick. So what we're thinking of when we're lifting something up, we're going to think of, well, what would it take to move the bucket just a little tiny bit? Like here's a bucket, doop, doop, just lifting up a little bit. So we're thinking of our distance as a very small change in our movement up, so that's our dy. And then our bounds is where do you start the bucket, where do you finish? So that's pretty free, that's 0 to 40. Now you have to spend your time in the force. That's where most of the work is going to be, is making sure we get the force right. And there are two things contributing to force. There's the bucket weight and there's the pulley weight. All right, so one thing that's going to happen is that the bucket is going to get lighter. So let's figure this out. Down at the bottom, it's 600 pounds. We've lost 200 pounds when we moved up. And so we say, okay, well, how much are we losing? Well, it says it's losing it at a constant rate. So if we say, well, okay, if you lost 200 pounds and you had 40 feet to do it, it's 5 pounds per foot. So we say, okay, so the bucket weighs 600 minus 5y. So here, this is the weight of the bucket, and so that's pounds. Pounds is a force measurement. So this is our bucket. The other thing is the chain, because the chain, it weighs something. Now, as you start out initially, you have 50 feet of chain. But as you move up, you have less and less chain to deal with. So how much chain do you have? Well, you could say you have 50 minus y feet of chain. Now, that's not a weight, that's a measurement of distance. How do you get the chain weight? Well, you know how many feet you have. You know it's 5 pounds per foot. So now you times this by 5. And then this, that's your weight of your chain, or that's the force. So the total is going to be the result when you add these together. All right, so what do we have? Well, 600, 5 times 50, that's 250, that's 850. And then minus 5y, minus 5y, minus 10y. All right, so that is our force. Okay, so there we go. And now we've done all the work. Well, no. The pulley's doing all the work. We've done all the setup. Okay, so we still have to find an answer because it doesn't say just set it up. We got to work it out. Well, all right. Might as well get to it. So we have the integral 0 to 40 of 850 minus 10y dy. That would be 850y minus 5y squared. You add 1 to the power of y, and that gives you y squared. Divide by that 2. And we're evaluating 0 to 40. 0. Beautiful number. That simplifies the computation a lot. So we just have to plug in the 40. So we have 850 times the 40 minus 5 times 40 squared, which is 40 times 40. Now, these look a little bit daunting, but it's not too bad. When you have a bunch of zeros, say, well, instead of thinking of it as 850 times 40, think of it as 85 times 4. And that seems a little bit simpler. 80 times 4 is 320, and then 4 times 5, well, that would be another 20, so that would get you 340. So 85 times 4 is 340. And they say, well, but wait, you have 2 more zeros, so you have 34,000. So 850 times 40, 340,000. All right, 5 times 4 times 4. Well, that's, again, I'm thinking I'll worry about the zeros later. And 5 times 4 is 20, times 4 is 80. And then add on your other 2 zeros. So you have 34,000. Subtract 8,000, which gets you to 26,000. Now, is that our answer? And why not? There's a gap, right? Because we need to make sure we include units in our final answer. So units for work tends to be foot-pounds. So if nothing else, get to the end and if you're like, this is probably almost surely wrong, you just write down foot-pounds and then say, okay, moving on. And at least you'll get that point right. But now, come on, we're going to get all the points. I believe in us. We can do this. We're ready. For 0 less than or equal to t less than or equal to 1, a wire follows the parametric curve. Okay, we're in parametric. X of t, y of t is 1/18, 6t squared plus 9 to the 3 halves, and 1/4 t to the 4. So we have our x and our y. And our density at a point, x of t, y of t, is given by a density function, t plus 1. Find mx, the moment with respect to the x-axis for the wire. Okay, cool. Now, we have some clues here. First off, we see the word wire. Wire tells us we are in one-dimensional setting. All right, that's good for us to know. And the other thing is we are after the moment with respect to the x-axis. You might say, well, how do you know that? Because it says that. And all right, so we're going to find that. And the good news is we don't have to find the mass. Whew, good. So we just have to find the moment. And we say, okay, well, we have that. And we do. So that's this M star. That's your moment thing. So what does that consist of? Well, you have distance, which really is location, but distance, usually people get along with that better. So location, density, measure. All right. So what's going to happen? Let's go through and write this all down, and then we'll go through and refine. So I'm going to start just the generic formula from the formula sheet. A, B, you had your distance, your density, and your measure. That's what it says. But let's adapt it to our situation. Now, in our situation, we say, okay, we have our mx. So that's going to be, the distance is going to be location with respect to the x-axis. Okay. The density is density. We'll come back and visit that in a second. And measure is length, because it's a one-dimensional object. All right, so we're making progress. And all right, let's do a quick little sketch here. Now, we don't know exactly what it looks like. Everything is very positive. And so let's just say it's doing something like this. Here is our wire. A picture doesn't have to be precise to be useful. Now, the idea is we're cutting our wire up into lots of little pieces and saying, all right, what's happening with this piece? So we say, well, what's our location with respect to the x-axis? And this is y. So remember, the moments are kind of strange. You see moment with respect to x, you put in y. You see moment with respect to y, you put in x. So you have to keep that in mind. Density is given. And we say, okay, well, in our case, that's t plus 1. Now length, we have to go back and say, which length? Well, there's 3 versions of length. We do the parametric length, because that's the setting we're in. So for length, we're going to have the square root of x prime squared plus y prime squared dt. And let's go ahead and just say what y is. Y is 1/4 t to the 4th. And go ahead and update our a and our b are 0 and 1. So we have essentially all of our pieces in here. We're going to have to work on this piece first. And the length is almost always the hard part because it has a square root. And so I think it's good for us to get some practice working and seeing how do square root terms, how do you deal with them? And so let's try it out. Okay, so brace yourself. Some computation is ahead. This is sort of really testing our algebra. So be ready. We can do this. We can do this. All right. Well, so I'm just going to work on x prime squared plus y prime squared. So x prime squared plus y prime squared. Okay, so here we go. X prime, well, we have the 1/18 stays there. The 3/2 comes down. We're doing chain rule, 6t squared plus 9 to the 1/2. And then, don't forget, you have to take the root of the inside, 12t squared. Y prime squared. Well, 1/4 times, the 4 comes down, t cubed squared. All right. Now, here's the thing. If you've lived a good, clean algebra life, nice things will happen. If nice things aren't happening for you, you should check your work. So let's see if nice things happen. In particular, we really are trying to build up to say, oh, all of these things combine together in a nice way. Well, here you can see the 4's cancel, Nice. 3 times 12 is 36. 18 times 2 is 36. So those all cancel. Nice. And okay, so what do we have? Well, because we have a square root here and square it, that gets us 6t squared plus 9. And then don't forget that t, because that's easy to forget. And then here, t cubed squared is t to the 6. Well, you can pull a t squared out. Might as well do that. And if you do that, and then here, I'm going to just sort of swap the order. You'll have t to the 4th plus 6t squared plus 9. Now, you're like, I'm happy with this. T to the 4th plus 6t squared plus 9. Does that factor in a nice way? Well, yes, it does. Oh, they like us. They really like us. What does this factor as? This factor as t squared plus 3 squared. And so keep in mind, right, in the back of your head, you're really looking for a plus b quantity squared. So you're thinking like, if you ever see 3 terms, you're like, okay, what is my a squared and what's my b squared and what's the 2ab? And that can help you figure out. You say, oh, well, there's my a squared, there's my b squared, and that's my 2ab. All right. So what does this tell us? Well, we really have 2 things multiplying together to square. So this is really t times t squared plus 3 squared. Okay, good. That was our hard part. Now we're ready to put it together. And what do we have? Well, so our moment here, we have integral 0 to 1, 1/4 t to the 4th. Okay, so that's our location. That's our location relative to the x-axis. We have our t plus 1. And then the square root of x prime squared plus y prime squared, because we got a square, that's going to become a t times t squared plus 3 and dt. All right. Well, everything's polynomial, so that's good news for us. We have a 1/4 t to the 4th times t, so I'll put those together, 1/4 t to the 5th. Now, let's multiply these terms out. T plus 1 times t squared plus 3. When you're integrating a polynomial, basically, unless you're really lucky, you have to expand. So let's do our expansion. T times t squared, t cubed. T times 3, 3t. 1 times t squared, t squared. 1 times 3, 3. And, all right, great. Now, we're almost there. The next thing is we got to put this t to the 5th in. And, okay, so if we do that, what do we have? Well, we have the 1/4. We'll go ahead and leave that out. Integral 0 to 1 of, well, t 5th times t cubed, t to the 8th. And I'm going to go ahead and swap the order here. T squared times t to the 5th is t to the 7th. T to the 5th times t is t to the 6th. And then t to the 5th times 3 is 3t to the 5th. All right, good. And now we're ready to integrate, term by term. So 1/4 times 1/9 t to the 9th plus 1/8 t to the 8th plus 3/7 t to the 7th plus 3/6. Well, let's go ahead and put that as 1/2 t to the 6th. Evaluate from 0 to 1. Okay, now, good news. When you plug in 0, you get 0. When you plug in 1, well, okay, you get lots of 1s, 1 to powers. So you end up with 1/4 times 1/9 plus 1/8 plus 3/7 plus 1/2. And at this point, you're like, oh, Do we have to get the answer to one fraction? You do not need to give the answer as one fraction. Now keep in mind, look at the instructions. Generically speaking, once you get to the end and you've done all your evaluations, you don't have to go and simplify. You can if you want, but if it does say simplify, you should. And sometimes when it says simplify, it's because the answer truly, truly is simple. And when the answer truly is simple, that's oftentimes a way for you to check if your answer is correct. So keep in mind, pay attention to what the instructions say to do. But for us, it says, hey, you don't have to get it down to one fraction. And we're like, nice. We are happy with this news. This is great news for us. And so what we're going to do is we're going to put a box and say, oh yeah. And we're done with number 9. One more problem to go. Our final problem. Find the area of the shaded region shown, which can be described in polar coordinates by theta goes 0 to pi, and 2 root theta sine theta less than or equal to r less than or equal to theta plus 2 sine theta. I kind of like this picture. It kind of feels like a big wave coming down. And we actually don't really need the picture because we know a couple things. We know it's polar coordinates because it tells us it's polar coordinates. We know we're after area because it tells us we're after area. And we know how everything relates. We know which curve is the nearby curve. In other words, if you say, let's start here. Oh, let me switch to a different color just to emphasize what's going on. If remember in polar, you always say, how does everything relate back to the middle, the center point, the origin? Well, coming out, you're going to hit a curve, then you're going to go, then you're going to hit a second curve. And of course, the question is, which one is the nearby curve, which one is the far away curve? But because of the inequalities, we already know. So here, the inside, or if you like, the near curve, that's your 2 square root theta sine theta. Whereas the far curve, that's the one that's way far out here. That's your theta plus 2 sine theta. Now, we are happy to know this because it's given to us. If it wasn't given to us, we could have figured it out. And we would just say, well, maybe like take pi halves. Plug in pi halves and compare the numbers and see how they compare when you plug it in. But we say, all right, great. Now, how do we do area? Well, we've got a formula in polar for area. So area is add up from alpha to beta 1/2, and you have a difference of squares. Now, that's the far part, subtract the near part. Now, if it happens to be that you go straight to the origin, g of theta could be 0. But we say, okay, great. So we have our answer, our area is 1/2, add up alpha to beta, our far piece, subtract our near piece, d theta. Now, I'm going to make some comments here. This problem did a lot for us. So it did a lot of the heavy lifting. It gave us alpha and beta for free because it told us a range for theta. Now, if the problem hadn't done that, we would have had to do some work. What's the work? Well, the work is where do the curves cross, set the curves equal, and solve. And that's a time when you can use your formula sheet. But for us, we say, hey, you know what? If you're going to do the work for us, we're not going to complain. So we're going from 0 to pi of the far part, theta plus 2 sine theta, quantity squared, minus the near part, 2 square root theta sine theta, quantity squared, d theta. All right. Now, this might make us nervous, but let's trust in the problem writers that they've given us a lovely problem. And we say, okay, well, hey, what happens? Let's do our algebra. we're going to do some expanding. So 1/2 integral 0 to pi. We have theta squared, or if you like there, a squared, 2ab. So 2 times theta times 2 sine theta gets us to 4 theta sine theta. B squared, 4 sine squared theta. Okay, that's our first term expanded. Minus, square the terms here. 4 and the square root and the square, they undo each other. 4 theta sine theta. And now it's like, whoa. You might have said, oh no, how does one integrate theta sine theta? Stay tuned. We'll be doing that in the near future. But for now, they cancel. Nice. And theta squared is great. We can work with that. And sine squared theta is a thing. We will actually talk more about how to deal with sine squared theta. Spoiler alert, it gives us to us as a hint for now. In the future, it won't be quite so straightforward. Okay, so this says, hey, what's going on? Well, we have sine squared theta is 1/2 times 1 minus cosine 2 theta. So what is 4 sine squared theta? So we can just make some notes here. 4 sine squared theta, multiply both sides by 4. So 1/2 times 4 is 2, so that makes 2 minus 2 cosine 2 theta. All right, so this is going to be plus 2 minus 2 cosine 2 theta. All right, good. And now all of these pieces are things we can integrate. And we see the end is in sight. We're enjoying the last bit of it. So we have 1/2 integral of theta squared, 1/3 theta cubed. Integral of 2 theta. Integral of cosine, positive sine. Well, there was a minus to begin with, so it still stays minus. So there's a sine of 2 theta. And there was a 2, but now we have to account for that 2. So we're going to divide by 2, and 2 over 2 is 1, so it ends up going away. Evaluate from 0 to pi. Now plug in 0. 0, 0. And sine of 0, 0. Plug in pi. We get 1/2 times 1/3 pi cubed. Plus, plug in pi into theta, pi. And now sine of 2 pi, 0. So, there we go. And I'll go ahead and distribute the 1/2 through. Why not? So we have 1 over 6 pi cubed plus pi. And our final answer to our final problem of our practice. Wow. And I should say, there are certain problems that you know they love. They love area and polar curves. They just love those problems. So you know it's coming. They love having something with a work. It could be pumping, could be lifting something up. They love center of mass or moment. You know, you kind of know what's coming. You have a good idea. So make sure you're practicing these problems. Now you may say, Steve, you took kind of a while to do this practice. We only get 75 minutes. But the good news is I go slow and I said a lot. I had a lot of commentary. And the test is doable. You can do it. You're amazing. Keep at it. Keep practicing. Be prepared. Know how to use your tools. Know what situations you're in. And you'll be all right. You'll be more than all right. You'll be wonderful. I believe in you. Thanks for coming. Thanks for practicing. Keep at it. And let's all have a good day at the test. I'll see you again. Bye.